Hello everyone. Up till now we have seen devices such as waveguides, cavities, which are nothing but resonators. Now today we will see another type of passive devices. These are called as T's, which are frequently used in the microwave communication circuits. So what is basically a T? These T's are known as microwave hybrid circuits. Hybrid in the sense are they are combination of two or more passive devices. So microwave circuit normally consists of several microwave devices. They are connected in such a way that we will achieve a desired transmission of microwave signal. So microwave communication circuit is not a single device. It's a combination of several devices. So many different devices we are using like transmission line, waveguides, resonators. Now we are getting introduced to T's and so many others. Okay, so these are combined in order to achieve transmitting our microwave signal in a particular way, whatever our requirement is. So the interconnection of two or more microwave devices may be considered as microwave junction. So this is what we can call a definition of microwave T's, that is interconnection of two or more microwave devices. It will be called as microwave junction, which are referred to as T's if their geometry is geometry is like English letter T. Okay, so commonly used microwave junctions include waveguide T's such as E-plane T, H-plane T, magic T, hybrid ring, which is also called as rat race circuit, direction coupler, and a circulator. So on your screen you can see the diagram of these different devices. First diagram is of E-plane T. Now T is a name given after its geometry. If you can see, this is a T, but it is like this one. So its main arm or collinear arm, it is called as, it is on the horizontal direction, and side arm, it is in the vertical direction. Okay, then there is a H-plane T. We will see the functioning or actual geometry in the later on in the video. So then there is a H-plane T, which is completely in the horizontal direction. All the arms are in the horizontal direction. Then there is a magic T, which is also called as hybrid T. It is a combination of E and H plane. So this is like this one. So E and H plane T are combined to provide magic T, and there is a hybrid ring which has a ring like structure and different ports along its circumference. So these are some of the waveguide T's. Now these T's are combination of two or more waveguides. As you can see, E-plane T, there is a rectangular waveguide here and rectangular waveguide again here. Then rectangular waveguide here and rectangular waveguide here in both E and H-plane T. So they are combined and created a junction, and that's why they are called as microwave junctions. Okay, here also there is a combination of different waveguides. Here there is a circular waveguide here and rectangular waveguides here. So it's called as hybrid ring. Okay, so let's look at the first T, that is E-plane T. Why it is called as E-plane T and what is its structure? So waveguide T's may consist of E-plane T's, H-plane T's, magic T's, hybrid rings. Then apart from these T's, there are several other devices such as corners, bends and twists. The diagrams that we have seen till now, all of them had a sharp edges, that is fixed structure like a T-like structure or a ring-like structure. These structures are created in order to transmit or carry the microwave in a particular direction. But sometimes your direction may not be horizontal or may not be vertical also. In T's, we have either horizontal or vertical direction like this one. Okay, but sometimes you require a transmission in a different direction like angle direction. So you may need a corners, or you need a transmission of microwave in a arced way. So you may need a bend, or it may be also a twist. like this one. Okay, so different direction in which the waves should be transmitted, based on that particular device may be chosen. So corner bends and twist we are not going to discuss, but other devices we will discuss right now. So first of all, in this E plane T and H plane T will be discussed. So in microwave circuits, a waveguide or a coaxial line junction with three independent ports is commonly referred to as a T junction. Okay, so a waveguide or coaxial line with three independent ports. Okay, as from the geometry you can see, there will be three ports, 1, 2 and 3. So 3 ports will be a T junction. Now, how can we analyze or characterize these particular devices? We know that at microwave frequencies, our normal parameters such as uh, ABCD parameter, H parameters, Z parameters, that is consisting of V and I, those won't work. For microwave devices, we prefer S parameters. Now, if S parameters are used for characterizing these T's, then what will be the size of S matrix? Now, for any microwave device, if it has a 2 ports, S matrix is of 2 by 2. Now in these T's there are 3 ports, so obviously the size of S matrix will be 3 by 3, that is third order S matrix. So 3 by 3 means total 9 elements, and out of these 9 elements 6 should be independent. Okay, so why that is, that we will see, or how it is, that we will see. The characteristic of this 3-port junction is explained by 3 theorems of the T junctions. These theorems are derived from the equivalent circuit representation of T junction. So whatever geometry that we have shown about rectangular waveguides or combination of rectangular or circular waveguides, that T can be represented in a circuit, and that circuit will be analyzed by the S parameters. So what are the theorems that are associated with these circuit? First statement of these 3 theorems, first theorem, or we can call it as a first theorem: a short circuit may always be placed in one of the arms of the 3-port junction in such a way that no power can be transferred through the other 2 arms. Okay, so what's the meaning of this? There are 3 arms to the 3-port junction. You will see that in the previous slide. Okay, 3 arms. So first one, second one, 3 ports, and this is a, these 2 are collinear arms, you can see, and this is a side arm that is on the second port. Second port has a side arm. So if you place a short circuit in one of the arms, no power can be transferred via other 2 arms. So if I place a short circuit in the, no power will be transferred via these 2 arms. That is the first theorem. Sorry. So a short circuit may be always be placed in one of the arms so that no power can be transferred to other 2 arms. The second theorem is now, the junction, if it is symmetric about one of its arms, a short circuit can always be placed in that arm so that no reflections occurs in the power transmission between other 2 arms. So if we consider normal geometry like this one, okay, if this part has a length equal to this part, then you can place short circuit over here so that this will be matched, and though there will be no reflection in the other 2 arms. So whenever you apply an input, if there is a short, then there will not be any reflection between the other 2 arms. That means maximum power will be transferred from first arm to the third arm, or first port to the third port, or it may be whatever it is, whatever this is first, second and third. If we consider first to the third, maximum power will be transferred because there is a short in here. Okay, so that is the second theorem. Then third theorem, it is impossible for a general 3-port T junction of any arbitrary symmetry, not necessarily equal arm's length, to present a matched impedances at all three arms. So considering the same geometry, it is impossible to generate a three-port junction to present matched impedances at all three arms. So you cannot provide any construction that will transfer maximum power from first port to second port, and at the same time second port to third port, or first port to third port. So maximum power cannot be transferred to the all ports at the same time. Okay, how or why this is, that we will see later on. So it's impossible to transfer maximum power in all the three ports. Okay, so let's look at the first type of T, that is called as E-plane T, or it is also called as series T. An E-plane T is a waveguide T in which axis of its side arm is parallel to the E field of the main guide. So let's look at the figure first. This is the figure 1. What is said? Axis of the side arm. What is the axis of the side arm? You can see here, this is a side arm which is in the vertical direction. Its axis will be like this. Axis of the side arm is parallel to the electric field in the collinear arms or other two arms. So electric field, as you can see, direction is vertical and its axis is a parallel to this one. So such T will be known as E-plane T. Now in the first port, the direction of E field is in upwards, so in the other port it will be downwards. How? Let's see that. The second statement, if the collinear arms are symmetric about the side arm, there are two different transmission characteristics. So what's the meaning of this statement? So should go to the next slide. So the collinear arms, which are these two arms, these two are collinear arms. If they are symmetric, that means this length equal to this length about the side arm. This is our side arm. So if they are symmetric about the side arm, then there are two transmission characteristics. So which are the two transmission characteristics? First one, input through the main arm. So here, if I give input in the first port, what will happen? And output will be taken from this arm. Input is given to port 1, output is taken from port 3 and port 2. Okay, you can see in the diagram A of figure 2. The second characteristic is input from side arm. In the first characteristic, or in the first way of transmission, you can give input to this arm also. So output will be taken from side arm and other collinear arm. Okay, so that is a possibility in first case also, input through the main arm. This is a main arm. Okay, now the second way in which you can apply the input is input through the main arm, side arm. So if input is given from the side arm, output will be taken from main arms. Okay, so it will go through this and it will go like this. Okay, so this is simple construction. So that is how two types of transmission are possible. So it can be seen from the figure that E-plane T is perfectly matched with the aid of screw tuners or inductive or capacitive windows at the junction. The diagonal components of scattering matrix will be 0 because there will be no reflection. So what's the meaning of this statement? So if I place a screw tuner at the junction on the side arm, okay, or inductive or capacitive tuner, if I place it here, remember the second theorem, if it is placed here, then maximum power will be transferred from first port to the second port because this is shorted or tuned, so matched condition is obtained, and because of this, what is it is said, diagonal elements of S matrix will be 0. Why? We know that in the S matrix, diagonal elements represent reflection coefficients. Since maximum power is transferred, that means there is no reflection. If there is no reflection, that means diagonal elements will be 0. Okay, so that is what it is mentioned in this particular statement. Okay, so if we match the side arm at a junction, maximum power will transfer, no reflection. Okay, and S11, S22, S33 all are 0. When the waves are fed into the side arm, that is at the port 3, the waves appearing at port 1 and port 2 will be in opposite phase but having the same magnitude. So that's the meaning. If we apply input here, output will be from here and here. So if electric field in direction is in the upwards for port 1, it will be in the downwards for port 2. That means magnitude will be same but the direction will be opposite, that is phase will be opposite. Okay, so that's the meaning of that particular statement. Okay, so let's move on to the analysis or characterization of this particular series T. So E-plane T characterization. Now first statement we are saying that this, because of this construction, S13 is equal to minus of S23. Now how this is assumed? Okay, what are the different S parameters that we can observe? Consider this particular diagram, that is figure 2b. Consider figure 2b. Now if input is given here, now where are the S parameters? Now at port 1 I will have S13, that is first port and third port. Here I will have S23, and here I will have S31, S32, and at the junction, if any reflection occurs, for that S11 here, S22 here, and S33 here. So S11, S22 and S33. Okay, so these are considered as 0 because no reflection assumed. So because of this, S13 is equal to minus S23. So how it is? Let's see. Forget about this. Now if input is given from port 3, output is taken from port 1 and port 2, that will be equal in magnitude but opposite in phase. So if equal in magnitude, S13 is equal to S23 but opposite in phase, that means S13 is equal to minus of S23. Okay, so that's the meaning, because output is divided into the two arms, considering this a symmetry. Okay, so that's the meaning of this particular assumption. S13 is equal to minus S23. So the meaning of this assumption is that this does not mean that S13 is always positive or S23 is always negative. You can write minus S13 is equal to S23 also. Meaning of negative sign is that they are opposite in phase. Okay, the negative sign does not represent algebraic negative. Okay, it is regarding the phase of the two particular parameters. Okay, the negative sign merely means S13. Here there should be correction, instead of SB there should be S13. Sorry, S13 and S23 have opposite signs. That's the meaning. S13 and S23 have opposite sign. For a matched junction, S matrix, now 3-port junction, that's why 3 by 3 order, S matrix is given by, now diagonal elements, these are reflection coefficients, all are assumed to be 0 because there is no reflection, that's what we have assumed. Then other elements are mentioned according to the matrix representation. Now recall the properties of S matrix. The first property, that is symmetry property of S matrix, tells us that symmetric terms are equal. So if we consider this property, S12 is equal to S21, S13 is equal to S31 and S23 is equal to S32, because we know S matrix has a symmetry property. Now if we consider this symmetry property, what about other properties? that is zero property of S matrix. What does zero property of S matrix tells us? The sum of products of each term of any column multiplied it by the complex conjugate of corresponding term of any other column is 0. That means if you consider S11, S21 and S31 here it will be S12, S22 and S32. So zero property means S11 into conjugate of S12, S11 into conjugate of S12, S21 into conjugate of S22. So that is here, and S31 into conjugate of S32, that is here. If we add all of these three, then it will be 0. Same thing you can do about second column and third column also. So that is zero property. So therefore S13 into S23, S13 will be here and S23 will be here. Sorry, S11, S12, S13, okay, and S21, okay, S12 into S23 will be 0. Okay, conjugate of S23 will be 0, and because of this either S13 or S23 conjugate both should be 0. Okay, now combination of symmetry property and zero property is used in this case. Okay, because of this one of them has to be 0 or both may be also 0, but unity property states that sum of the products of each term of the any one row or column multiplied by its complex conjugate is unity. Now what is unity property? Again, sum of the products of each term of any one row. So what are our rows? S11, S12, S13. Okay, so S11 is 0, forget about it. So S12 multiplied by S21, S22 is 0, then S23. Okay, so if we take particular column, what will happen? S11 is 0, S31. So let's consider only one column for understanding. I am considering only one column, that is first column, S11, which is 0, S21 and S31. What does unity property says? This is 0, so ignore it. S21 into its conjugate, S21 conjugate, this is there, plus S31 and its conjugate, that is S31 into S31 conjugate, this is equal to 1. Similarly, you can apply this property to other two columns as well. Okay, so if we substitute results of symmetry property in above equations, what we can say? S21 and S12 are equal. So here I will put S12, so it will become mod of S12 square is equal to, I take this term on the right hand side, 1 minus mod of S13 square, because S31 is nothing but S13 from the symmetry property. So 1 minus S13 square is equal to S12. Similarly, 1 minus S23 square is equal to S12. Same thing will happen in this case also. Okay, because S13 into S13 conjugate, that will be S13 is equal to S31 and S31 is here also. So this is the equation that we will get if we substitute symmetry property in these equations. Okay, so from these equations, what we can say, this is contradictory, because at the beginning what we have assumed, SV13 is equal to minus of S23. Now does it apply over here? If S13 is 0, then S23 will be also 0 because of this statement that we have initially assumed. Dividing of the wave or power into two equal arms, equal magnitude, opposite direction. Now because of this we have assumed this one. Now if S13 is 0, S23 is also 0, or if S23 is 0, S13 is also 0. So if we substitute that here in these two equation, that will not be equal to S12 because it will be equal to 0, or this will total will be equal to 1, not 0. 1 minus 0, it will be equal to 1, and S12 will become 1. So this is contradictory. So above result of substitution is not true. So this inconsistency proves that the statement we have made, that it is third theorem, T junction cannot be matched to the 3 arms. So why have we done this, all the assumptions and properties? To prove the third theorem, which states that all the 3 ports or all the 3 junctions of the T cannot be matched to the perfect power transfer. Okay, in other words, diagonal elements of S matrix of T junction all cannot be 0 at the same times. So whatever we have assumed in the S matrix previously, that all 3 are 0, that cannot be true. 2 can be 0, but this cannot be 0. Or if these 2 are 0, this cannot be 0. So all 3 of them cannot be 0 at the same time. That's the conclusion of this all the calculation. Okay, so what will be the S matrix? So when an E-plane is constructed of empty waveguide, nothing inside it, that means no dielectric medium, and generally it is poorly matched in that situation. So hence all the diagonal elements are not 0, that we know now. Therefore collinear arms are usually symmetric. We know that nobody constructs a T where collinear arms are asymmetric. So if it is true that collinear arms are symmetric, then S13 will be equal to S23. Okay, that is considering only the magnitude, and S11 will be also equal to S22 because of maximum power transfer. So what's the meaning? If this is my T with these two arms of equal length, then S13 is equal to S23 considering only the magnitude, and here I have S11 and here I have S22. Both will be also equal because all that power will be transferred from first arm to the second arm, and that's why there is no correlation, there is no reflection coefficient and no reflection, both will be equal. Therefore S matrix can be simplified to, we don't know about or we don't care about third arm, so its matrix can be simplified to this particular matrix. Here you can see S11, and instead of S22 we have mentioned S11 again, and similarly symmetry property is observed here, S12 S12, here S13 S13 because of symmetry property, and S13 is equal to minus S23 or vice versa, S23 is equal to minus S13. That's why here minus S13 and minus S13, and this S33 is different. It is not 0, it is not 1, it may be having some value. So this is the final representation of S matrix for any T constructed from the waveguides. Okay, this can be used for analyzing the performance of this particular what we can say E-plane T. Okay, so this is also called as series T. Let's look at the H-plane T. Now it is also called as shunt T, as you can see in the diagram. A shunt T is a waveguide T in which axis of its side arm is this one. So what is the axis? Axis will be this one, is shunting the E field. E field is in upward direction, axis in the horizontal direction, so there is a normal or perpendicular between these two, so that is called as shunting the E field, or parallel to the H field. If E field is in upward direction, H field will be in these two directions, so parallel to the H field of the main guide as shown in figure. Okay, so that is what's the meaning of HT. So what's the difference? How does it make the difference? It can be seen that if two input waves are fed into port 1 and port 2, so if I input here and here at the same time, what will happen? Output will come from here. Okay, so since there are two inputs, both directions are upward, I have taken, so output will be also here and it will be additive. So output at port 3 will be in phase, same direction as the port 1 and port 2 electric fields, and it will be additive. So addition of these two inputs will be output of port 3. Or on the other hand, if we input the port 3 here, electric field will be divided into two ports into equal halves, split equally into port 1 and port 2. Both will be same magnitude and same phase. They will not be out of phase. Okay, so you are seeing upward direction at the both ports. Okay, so hence the S matrix of H plane T is similar to E plane equations, except S13 is equal to S23. In the E plane we mentioned S13 is equal to minus S23. Now here S13 is equal to S23 because this both are having the same phase. Okay, so if you compare E plane T with the H plane T, what will happen? What is the difference? Electric fields are in phase in H plane T, electric fields are out of phase in E plane T. Okay, so that's why S13 is equal to S23. Other equations will remain same. So what will be the changes in the S matrix? Here for H plane T we will get plus 1 S13. Okay, apart from that every other term will remain as it is for H plane T. Okay, so that is regarding waveguide T's, E plane T and H plane T. That's all for today. In the next session we will see magic T and hybrid ring. Okay, thank you.